So it's a great honor to give this talk, obviously. Like many people in my generation, I first got interested in this subject because when I was a boy of something like 13, a family friend gave, let's see, I think I have it here, gave me a copy of this book. But somehow, even more important, possibly, for getting into this field was a present I received a few years later, which was actually this book. And unfortunately for you, this talk is more in the style of this book than it is in the style of this book. But in some sense, this talk begins in the context of classical general relativity, where this book leaves us off. But nonetheless, I think it's important to start from the perspective of this book, and if you want, the formulation of cosmic censorship in this book is precisely what's written here. God abhors naked singularity, and the purpose of this talk is to try to discuss the progress in, first of all, formulating this dictum, and secondly, investigating whether it's actually true. So let me give you a brief outline of what I plan to say. So I'm going to begin with some background, and in some sense, I'll sort of first review the old story that we all sort of learn about, for instance, in this book, about cosmic censorship from the perspective of the Schwarzschild and then the Reiser, Nordstrom, and Kerr solutions. And then after sort of reviewing the old story, I'm going to sort of try to present what I'll call the modern reformulation of these conjectures. And the modern reformulation, the difference from the sort of the older story is that it really takes to heart the language of the initial value problem. And somehow initial value problem was very new in some sense when this was written. It was something that only pure mathematicians who study hyperbolic PD would think about. But now in the world of numerical relativity that we just heard about, actually initial value problem is what everyone thinks about when they think about classical GR. So it's not really exotic. And this is really the way that one has to understand these conjectures. So a lot of what we know about these conjectures sort of results from work in spherical symmetry. So I'll review a little bit of that, and then I'll try to take us beyond symmetry, and finally sort of give you a taste of what is the status and what is the perspective for further progress on these issues. All right, off we go. Schwarzschild, Reiser, Nordstrom, and Kerr. And this should be familiar to most people here. So Schwarzschild, or better, maximally analytically extended Schwarzschild. So that's the thing that you'll see in this book. So this spacetime, of course, was understood, well, originally by Singh on the basis of earlier work by Lemaitre, and then it became very well known through the paper of Kruskal. This is its Penrose diagram, and what we all know, what we all are taught, is this has a singularity, a true singularity, a curvature singularity at r equals 0. Moreover, this singularity is space-like in some natural sense, so we all learn this. And finally, it's cloaked behind an event horizon, H+, and sort of one way of saying that in the language that we all learn is that if you look at the past of future null infinity, the past of Scry plus, then that does not intersect this singular boundary. Okay? So those are the words that are written on this slide. Okay? So this is the prototype, if you want, of a singular spacetime. But we also learn in our Hawking and Ellis that singularities need not be cloaked behind horizons. And the quintessential example of such a singularity is negative mass Schwarzschild. And so negative mass Schwarzschild, so the usual Schwarzschild metric where the mass parameter is negative, has Penrose diagram depicted here. So again, R equals 0 is a curvature singularity, but now, in some natural sense, it's time-like. And moreover, it's visible to infinity. And it's visible to infinity, for instance, you can say naively that you look at future null infinity, I plus, you look at its past, the singularity is in fact completely contained in the past of future null infinity. So this is the textbook naked singularity. Okay. But there's another example of a time-like singularity, which in some sense is even more surprising. And this is contained deep inside, again, the maximally analytically extended Reiser-Nordström, which is drawn here, or Kerr black holes. So again, these pictures are in our Hawking analysis. And in the Reiser-Nordström case, this maximally extended spacetime was first understood by Graves and Brill, and in the Kerr case by Cambridge's own Brandon Carden. So, so here again, we have a time-like singularity at R equals 0, okay? But it's deep inside the black hole. So in particular, it is not in the past of future null infinity. So it is not naked in the sense that it's seen by faraway observers. But the fact that it's time-like means that you can think of it as being locally naked. And what does locally naked mean? Well, it just means that, well, if you're an observer, sort of, I'm not old enough to, yeah, well, you all know. If you're an observer that sort of passes right to the left of R equals 0, then in your, okay. So even though you don't see it at infinity, if you're an observer like this, okay, the fact that this is time-like means that there are, for instance, null curves going back that go into the singularity. Okay, so everyone knows all of that. So now, from this point of view, what are the cosmic censorship conjectures as we sort of learned them in the old days? Well, there are two sort of versions of the cosmic censorships that conjectures that develop, what is commonly known as weak cosmic censorship, and then something that's commonly known as strong cosmic censorship. And the old style formulation, if you will, of weak cosmic censorship is the statement that in gravitational collapse, singularities are always cloaked by horizons. So, particularly, you will not see the singularity in the past of future null infinity. So let's go back. Well, what about this example? I just gave you an example of a spacetime which had a naked singularity. Well, the conjecture says in gravitational collapse. So gravitational collapse means collapse from a regular situation. This naked singularity is eternal. At any given time, you have an example. So somehow this was not in contradiction with believing in this conjecture. And then there was the so-called strong cosmic censorship that sort of developed a few years later. So again, these conjectures both originate from Penrose. And this says that in gravitational collapse, generically, there are no locally naked singularities. That's to say, singularities are generically space-like or null, but not time-like. So these are the way in which this was typically presented. And of course, this, you can think of it, and we'll sort of return to this issue later. I mean, this is a spacetime that does arise in gravitational collapse. Okay? So, on the other hand, it has locally naked singularities. So clearly, if this is going to be true, you have to add an extra word, and the extra word is generically. Now, was this just wishful thinking? No. There was some vague evidence for this latter conjecture, and again, this vague evidence is sort of known, well known to most people in the audience, sort of this blue shift instability, which was again first really discovered by Penrose, associated to the so-called inner horizon, the inner horizon, which you can see here, and more about that inner horizon later. So this is sort of the original, what I'm phrasing, old-style formulations of cosmic censorship. Well, actually, here I said, as far as strong cosmic censorship is concerned, that singularities are generically space-like or null, not time-like. But you can actually strengthen this statement, and for want of a better name, I'll call this very strong cosmic censorship. And in very strong cosmic censorship, you say in gravitational collapse, oh, there should be a generically here. Generically, singularities, oh, it's there. I didn't underline it, and I forgot. Singularities are generically space-like. And this also meshed with something which is called the BKL picture, which, well, in some interpretations of what that was meant to say, it meant that not only are they space-like, but they are of this and this form. Okay. So this is sort of the received conjectures from the classical period of black hole physics, if you want. So now I want to present sort of the more modern way that we think about these conjectures. This is not, in opposition to the old style. It sort of clarifies sort of the statements as I've presented them there. But sometimes purely for semantic reasons, but sometimes also for more profound reasons, it's actually important to get the statement exactly right. So what is the key to the sort of modern formulation of the cosmic censorship conjectures? So in some sense, the key to formulating these correctly is accepting once and for all the primacy of the Cauchy problem. So this is very important in saying anything about general relativity. So we are very fortunate in the context of general relativity to work in a theory where there is a well-defined sort of map between initial state and space-time that develops from initial state. And there were some subtleties in sort of achieving that map, so only really was sort of completely understood in a paper of Madame Choquet and Bob Garrosh from 1969. But somehow this is what makes general relativity a predictive theory, and in some sense all conjecture should be stated in terms of this. And I remember when I was a first-year graduate student at Princeton of Dimitrios Christodoulou, one of the first things he told me is you have to unlearn everything and relearn it from the point of view of this theorem. So let me just recall what this theorem says. It says, so I'll only talk for a second about the vacuum equations. So there's a notion of vacuum initial data set. You give me a vacuum initial data set. There's a unique smooth space-time satisfying the Einstein equations that evolves from it. Okay? So it should be satisfying the Einstein equations. Ricci curvature should be 0. It should evolve from the data. So that means it should be globally hyperbolic. This is a condition that means that the solution is indeed determined uniquely from the data. Okay? Having the data as a Cauchy hypersurface. And moreover, it should be maximal. It should be the biggest globally hyperbolic spacetime that evolves from the data in this sense. Okay? So there's a funny story for those of you who are interested in things like this. The original proof of this was non-constructive. It appealed to Zorn's lemma. That also gave this theorem a sort of reputation of something exotic. But actually, a bright young research fellow in Magdalen College here in Cambridge successfully de-Zornified this theorem. So the fact that general relativity is predictive is it's a constructive statement. Anyway, so similar theorems can be proven for suitable coupled Einstein-Mather systems like Einstein-Maxwell, Einstein-scalar field, Einstein-dust. And this also should remind us that, we first, if we want to sort of study general relativity as a predictive sort of theory, then we have to first decide once and for all what is the Mather in question that we're dealing with, form a closed system, and then sort of consider the initial value problem for that closed system of equations. All right, so what does it mean to take to heart the sort of dynamic Cauchy problem approach to think about these questions? So the first thing is the following. Assumptions can only be made at the level of initial data. So you never assume things about space-time. Okay? Space-time is a product of initial data. You can only assume things about initial data. Okay? So any assumption, generic, this, I don't know what, asymptotic, it's an assumption on initial data. Okay? And the second thing that you have to take to heart is that, well, sort of the only object that you have is the maximal Cauchy development of your initial data. So any property that you want to talk about has to be a property that can be expressed in terms of this maximal Cauchy development. So in particular, let me say already a comment. Because the maximal Cauchy development is globally hyperbolic, by definition, then its finite boundary, whatever that's supposed to mean, can never be time-like. Okay? So somehow there is no such thing as a time-like singularity, period, by definition, trivially. Okay? So whatever cosmic censorship is supposed to be, it cannot be the statement that singularities are not time-like, because they are not time-like by definition. So we have to go back to all these examples and rethink what's the right way to formulate what we were trying to formulate. Okay? All right. So let's go back to all our examples, and let's start with Schwarzschild. So here is the Schwarzschild that we know and love. So how do we think about this dynamically? So pick your favorite two-ended hypersurface, like this sigma. And, well, of course, Cauchy evolution you can do in the future and the past. You can do both. But I'm a progressive person, so I'm only going to talk about future evolution from now on. Okay? So pick this hypersurface sigma. Its future Cauchy development is the darker shaded region here. Its past, so future and past Cauchy development would have been the whole maximally analytically extended Schwarzschild. Okay? So it's the same object that we had. I haven't changed the object at all. But I stress, never again should you think of this as maximally analytically extended space-time. Okay? It is not maximal, that's irrelevant. Okay? Irrelevant. You should always think of this as the maximal Cauchy development of asymptotically flat two-ended data. Okay? Of course, two-ended data is not physical per se, and we will discuss this issue later in the talk. Okay? But sort of that being said, you should think of sort of this space-time as the maximal Cauchy development of two-ended data. Okay? That's how we should think about Schwarzschild. Okay, so with this being said, let me review the nice properties of Schwarzschild that we know and love, but let me just say them again in this more sort of dynamic language. Okay? So the data is complete. There's nothing wrong with the data. You can quibble about the fact that it's two-ended, and indeed, that's not physical, but it's sort of, for pedagogical purposes, it's fine for the purposes of this talk. So the data is complete asymptotically flat. There's nothing missing in the data. Nonetheless, this maximal Cauchy development is future geodesically incomplete. Okay? This is a non-trivial statement because this is a maximal Cauchy development. Okay? Moreover, here's another non-trivial statement, which you can phrase very nicely in terms of the Cauchy problem. This incompleteness property is stable to perturbation of initial data. Okay? So Penrose's singularity theorem and Cauchy stability tells me I perturb the data, the solution will still have what's known as a trapped surface, and on account of that and the fact that it's globally hyperbolic, it will be again geodesically complete. So completeness is not a fluke. This was a very important realization in the history of the understanding of singularities in general relativity. Another important feature is the following, and Gary Horowitz is here in the front row. Future null infinity is complete. So even though the space-time is geodesically incomplete, future null infinity is complete. So future null infinity is the arena of gravitational wave experiments. It means gravitational wave experiments can go on for as long as they're funded, and in view of the success of last year, it seems that that will be effectively forever. Actually, this notion of completeness, and we'll refer to this again very, very soon, as far as I know, it really goes back to an old paper of Bob Garrosh and Gary Horowitz. Maybe that was from your thesis even, I don't know. But this is actually an important thing that sometimes is not emphasized enough, but this is actually crucial. Moreover, the spacetime is truly singular. Okay, we said that r equals 0 is a curvature singularity. So a more sophisticated way of saying it is that you cannot extend this manifold as a twice differentiable C2 in mathematical language, Lorentzian manifold. But in fact, Jan Zbierski, who I mentioned earlier, has shown that you cannot extend it as a continuous Lorentzian manifold. So that means that observers not only see a curvature sort of singularity, but they are physically torn apart if they fall on r equals 0 by infinitidal deformations. So actually this statement, it sort of was a folk theorem. There are 2 words in this book that contain that statement, but the first proof is due to Zbierski. And finally, as I said, you can think of this singularity as forming some sort of a space-like boundary S of space-time. Okay? So this is Schwarzschild from the point of view of Cauchy evolution. Let's think, though, of negative mass Schwarzschild, because this is maybe less familiar. So let's pick in negative mass Schwarzschild a hypersurface sigma, which is sort of as big as it can be. So here is one. Now, such a hypersurface will be asymptotically flat towards this end, but it will be incomplete towards here. And in fact, as you go in this direction, the curvature will blow up. But no matter, it's a hypersurface. Okay? You can think of its maximal future Cauchy development, and the maximal future Cauchy development is precisely the shaded region here. It's precisely that. So we are taught we only can talk about the Cauchy development. So we erase everything else. This is the Cauchy development. Can we understand everything from the point of view of the Cauchy development? So in particular, how can we identify this as possessing a naked singularity? Well, okay, you can start saying, of course, by definition, the past of null infinity cannot contain the singularity. You cannot talk about that anymore. You could try to say, well, the closure of the null infinity, etc. But actually, Gary Horowitz, in some sense, showed us the way to understand, from this point of view, why this has a naked singularity. If you just look at this piece of future null infinity, okay, then it's incomplete. Okay? So if this was the space-time arising from this data, and LIGO was doing its great gravitational wave experiments, at a certain point, the experiments would have to stop. So it turns out that this is an alternative way of thinking about what it means to possess a naked singularity. And you can talk about this without ever touching the singularity, saying this is the singularity. Okay? And that's quite attractive. It's confusing at the beginning, because when you think of this as negative mass Schwarzschild, then future null infinity is complete. Okay? But if you think about it dynamically, this is the right way of saying.
For negative mass, it should be space-like singularity.
Not for negative mass, no.
For negative time-like, should be time-like.
It's here it's time-like.
But it's time-like, or it's within.
Here there are no time-like singularities once one adopts determinism. So this is how one now thinks about what it means to possess a naked singularity. What about the locally naked singularity? Because, of course, locally naked, the way we said it before, was that the singular boundary was time-like. So how do you say this now when you're not allowed to draw that sort of extension? Well, you say the following. If you look at this maximal Cauchy development, then it has what's known as a Cauchy horizon. More about the origin of this term in just a second. And the maximal Cauchy development is extendable to a larger space-time across this Cauchy horizon. The Cauchy horizon becomes a null hypersurface in the extension. Okay? It's just that these extensions are not globally hyperbolic. They're not uniquely determined by initial data. In fact, they're severely, severely non-unique. Okay? So in some sense, this also emphasizes what was really bad about time-like singularities in the old picture. Okay? And it's the fact that they indicate a failure of determinism. And in fact, the reason why it's not correct to draw this picture and then say you have a time-like singularity is precisely by drawing this particular picture, you've already made an arbitrary choice, which has nothing to do with initial data. Okay? So it was not, in some sense, correct, though it is pedagogically useful to think about there being a particular time-like singularity. Okay. So all this is great, but we still don't have to worry about the existence of negative mass Schwarzschild, because we're allowed to reject spacetimes on account of some property of their initial data. And in this case, the initial data itself is incomplete, so we are allowed to rule this spacetime once and for all as inadmissible. Fine. Let's go now back to Reisner-Nordström or Kerr. Let me sort of draw here again Reisner-Nordström. So again, this is my favorite initial data hypersurface. So I think I'm looking at this, and I want to know what is its maximal Cauchy development. Its maximal Cauchy development is precisely this darker shaded region here. So again, we throw away everything. This is the only thing we're allowed to talk about. Just as an aside, so this is again a picture of the same thing in Kerr. And you know, in Kerr, often one draws, so this is what's drawn here, some slice of the sort of, some two-dimensional slice, space-like slice of Kerr. But actually, the previous speaker in his master's thesis, together with Werner Israel, taught us the right way to think about the Penrose diagram of Kerr. You should think about it as sort of the domain of a double null foliation. So this is actually my interpretation of this picture in the Kerr case. So this is Reisner-Nordström or Kerr, thought of as a maximal future Cauchy development. Okay? And now the point is the following. These spacetimes, just like negative mass Schwarzschild from this point of view, they are future extendable, in fact, as smooth solutions of their sort of equations, vacuum equations, and Einstein-Maxwell, but these extensions are not globally hyperbolic and thus severely non-unique. Okay. So in particular, and I emphasize this 100 times, do not think that there is a time-like singularity going there. Because there is no principle that tells you should you draw a time-like singularity, a bunch of elephants, or anything else. Okay? Nothing tells you that there's anything there. And in fact, somehow, the Reisner-Nordström and Kerr, they are not just extendable, but they are extendable such that all incomplete geodesics, so all geodesics that only lived for finite time, can pass safely into the extension. And in fact, the curvature that those geodesics see is bounded, it's uniformly bounded. Okay? So there is nothing singular about Kerr or Reisner-Nordström. You should think of these as spacetimes that do not have singularities. Okay? And in fact, what Penrose's singularity theorem applied to these spacetimes is telling you, okay, is not that there's a singularity, it's telling you that determinism fails. Okay? And you really should think that in these examples, determinism is failing without there, in principle, being anything to do with singularity. So really the first person to understand this is Stephen Hawking. And one of his early papers back from 1967 was to try to formulate some more sort of general singularity theorem that would say that somewhere later on, possibly much, much later on, or maybe even earlier on in the past, there was something somewhere in the spacetime that's singular. Okay? So it's not really possible to formulate a truly good theorem that says that finally. This is really the best type of result that you can get. But actually, the whole terminology of Cauchy horizons, as far as I know, arises from this paper of Stephen. Okay? And he was really, I think, the first person to understand that Penrose's original theorem is not fundamentally a singularity theorem. So let me very quickly give you a modern formulation of weak cosmic censorship, and I'll just give you the first attempt here. So I'll take to heart Gary's sort of contribution in understanding the importance of the completeness of null infinity. So a first attempt at this formulation is the statement that for complete asymptotically flat vacuum initial data, the maximal Cauchy development has a complete null infinity. Okay? So this is a very nice statement. You don't even have to be able to talk about singularities, singular boundaries, etc. You can say it all in terms of null infinity. Whatever happens, gravitational wave experiments, they go on forever. And when you say it like this, then you realize that this is secretly a global existence theorem in the language of PD, which is still compatible with the singularity theorems of Penrose and Hawking. So this formulation, as given here, is in a very nice survey paper of Dimitri Christodoulou in Classical Quantum Gravity from 1999. But in some sense, you can think of it as also arising from this early paper of Bob Garrosh and Gary Horowitz. Okay, this first attempt will have to be corrected later, but in any case, strong cosmic censorship from this point of view is the statement that for generic, complete asymptotically flat vacuum initial data, the maximal Cauchy development is future inextendable as a suitably regular Lorentzian manifold. Okay? So when you say it like this, then you see that this is really a conjecture about uniqueness in the language of PD, or if you prefer more philosophical language, determinism. And again, this formulation is taken from the paper of Christodoulou. So interestingly, with these modern formulations, this is no longer necessarily a stronger statement than this. Okay? They're different. One is a statement of global existence, the other is a statement of global uniqueness, but this is really, in some sense, what the conjectures were sort of secretly getting at. Let me give you the formulation of very strong cosmic censorship from this point of view. You want to say that sort of very strong cosmic censorship is the statement that the space-time boundary is space-like. And you can make this statement in this context, even though it's sort of not necessarily clear how, in great generality, you can define the notion of a space-like boundary. But anyway, this is part of the conjecture. But if you think of strong cosmic censorship, very strong cosmic censorship, as saying that, you know, space-time should be like Schwarzschild, okay, and not anything like Kerr, Reisner, Nordstrom, then you can sort of formulate this as the statement that space-time, the maximal Cauchy development of generic asymptotically flat initial data, all right, will be inextendable in the same way that Schwarzschild was inextendable. That's to say, in a very strong way. Observers are not only do they observe infinite curvature, but they are in fact destroyed by infinite tidal deformations. Okay, so these are, if you want, the modern way of thinking about both weak and strong cosmic censorship. So, because I don't have so much time, I'm going to take from spherical symmetry only one lesson, and I'll go straight to beyond symmetry. So the lesson that I want to take from spherical symmetry is the following. So there's been a lot of work, as many people know, on cosmic censorship and spherical symmetry. In fact, most of our intuition comes from spherical symmetry, and in particular, sort of the first, if you want, work which exhibits the sort of picture, the conjectured picture of gravitational collapse, which is consistent with cosmic censorship, is the gravitational collapse model of Oppenheimer-Snyder, that's to say gravitational collapse of a homogeneous dust ball. And this sort of Penrose diagram is consistent with all formulations of cosmic censorship that I gave. But life is not that simple, and in particular, and I'm going to skip to this, Dimitris Christodoulou proved back in 1990 that for the spherically symmetric Einstein scalar field system, and the point about the scalar field system is that it's the best, it's the closest thing to the vacuum, sort of, if you're going to impose symmetry. What he showed is that there exist complete asymptotically flat initial data, so here is the data, such that their Cauchy developments look either like this or like that. So he constructed examples of initial data which were completely regular and fine, complete and all that, which gave rise to this space-time, and examples that give rise to this state. So in this example, future null infinity is incomplete. Okay? In this example, future null infinity is complete, but in both examples there is a Cauchy horizon beyond which the space-time is extendable. Okay? So if you want, because these are just examples, these are not a problem for strong cosmic censorship. Strong cosmic censorship had the word generic in its formulation, but weak cosmic censorship did not originally. Okay? So in particular, these examples tell you that, as I formulated, weak cosmic censorship is not true for the Einstein scalar field system under spherical symmetry. And there were some subsequent numerics concerning these naked singularities by Cheptuik. So the second attempt at weak cosmic censorship, it's very easy to fix that. If all you have is sort of some bad examples, you just add in generic also to weak cosmic censorship. So this is sort of the definitive formulation of weak cosmic censorship for generic complete asymptotically flat vacuum initial data. The maximum Cauchy development has a complete null infinite. Okay, so fortunately, a few years later, again, Dimitris Christodoulou showed that both weak understood now with genericity, and in fact very strong cosmic censorship, are true for the Einstein scalar field system under spherical symmetry. Okay? So for generic spherically symmetric initial data, what he showed is that the maximal Cauchy development has Penrose diagram that looks like this, such that future null infinity is complete, the singularity is space-like, and the space-time is inextendable beyond that singularity. Okay, so let's, in the last 2 minutes, go, as promised, beyond symmetry, and I'll tell you what the story is. So a partial result on weak cosmic censorship would be to prove the nonlinear stability of the Kerr solution. So let me explain why. So this is still a conjecture. If weak cosmic censorship is true, then in particular it should be true for a whole neighborhood of Kerr initial data in the moduli space of solutions of the Einstein equation. So in particular, here is the conjecture of sort of Kerr stability. If I look at initial data to the Einstein vacuum equations, which is close, so this is the initial data, I should say, which is close to the initial data that gave rise to the Kerr metric, the conjecture of Kerr stability is the statement that the maximal Cauchy development will have complete future null infinity. And in the past of future null infinity, which is this lighter shaded region, okay, the spacetime will approach two nearby Kerr solutions asymptotically. Okay? So in particular, even to say these words, you need to talk about null infinity, and it's only an interesting statement if null infinity is itself complete. Okay? So this is a major open conjecture in general relativity. It will be proved, I think, within the next few years. It's exactly the type of statement that can be proven now with sort of mathematical technology in general relativity. And in particular, in view of this, it says that weak cosmic censorship is true in a neighborhood of Kerr. So this is the theorem that I'm going to end with. So mathematicians hate to assume things that are not necessarily true, but I'll make an exception, and I'm going to assume that the previous conjecture is true. And I don't feel so bad in doing that, because I've never met a single person who, I've met people who have told me all sorts of crazy things, but I've never met someone who has told me that they don't believe that this conjecture is true. So let's pretend that it is true. Together with Jonathan Luke, we proved that if that conjecture is true, then very strong cosmic censorship is in fact false. And what we proved is that if the exterior of the Kerr spacetime is stable, then its entire Penrose diagram is also stable. And moreover, the resulting sort of spacetime is extendable beyond a bifurcate Cauchy horizon as a Lorentzian manifold with continuous metric. So you might ask, what about the sort of more physical one-ended case? More generally, a corollary of our theorem is the following. Any spacetime that has an exterior that asymptotes to a Kerr metric, which according to the final state conjecture talked about by Franz, would mean any spacetime that does not disperse completely, will have the property that there will be a piece of Cauchy horizon in the black hole interior across which the spacetime is continuously extendable beyond. So in that sense, null boundaries of spacetime across which the spacetime is in fact extendable are ubiquitous in general relativity if you believe the final state conjecture. All right, well, let me not say sort of what are the open problems that are sort of suggested by these, because I think everyone can infer them for themselves. Let me just end by wishing Stephen a happy birthday. Thanks.
Questions? Slava.
Yeah, assume that general relativity should be modified, and not even in Planckian scales, but you could modify theory classically as a scale 3 order of magnitude or 5 below the Planck scale. Then you can avoid all the singularities there. How this kind of statement as theorems would be modified, okay, in such a theory without singularities? Because I understand that for singularity you can always hold black hole singularity. You can say that it's hidden by horizon. But if, for instance, they reach some maximal curvature, then I don't know even how to formulate these theorems.
Well,
What will be hidden? Because there will be no singularity, and the space will be Cauchy complete. You can go beyond the singularity. So you cannot prove in this case, if you don't apply general relativity, if you have broken theorems, for instance, for this strong energy condition, etc., you cannot actually use this kind of language because space-time can be so-called geodesically complete,
well,
even in the presence of horizons.
somehow, again, the point in sort of making all these conjectures, formulations about sort of classical general relativity is that, okay, this is a theory that in some sense we believe in its regime, and it's much cleaner to make statements about classical general relativity that we can then, after we make the statements, we can sort of ask ourselves, for how long does one believe this statement, etc.
That actually it's completely non-valid for sure when you approach Planckian curvature.
Well, so first of all, one thing to remember about the Kerr solution, and this is in fact the whole point of this conjecture, if you want, is that it is not singular. So there is no Planck curvature. If you look at the correctly at what the Kerr solution is. Well, Schwarzschild is non-generic, though.
What do you mean non-generic?
Well, in the Kerr family, it is already non-generic. So any definition of non-generic, you don't have to be a pure mathematician like me to understand that Schwarzschild is non-generic in the Kerr family. So there is no curvature singularity in Kerr. The whole point of this conjecture is to say that when you perturb, something, quote, bad happens, which is actually good, because the failure of determinism is perceived, rightly or wrongly, to be worse than having curvature singularity. Now, if one wants to put some cutoff and say, I only believe general relativity until something bad happens, and if indeed something bad happens, sort of like something bad happens in Schwarzschild, or in Oppenheimer-Snyder, it doesn't matter, I prefer the one-ended case anyway, then what this means is that there is some, again, space-like curve here, a little bit before r equals 0, and general relativity tells you that you go there. That's a very non-trivial statement. The geometry is in a very non-trivial state, a little bit before r equals 0, and, okay, what happens later? You have to formulate a better theory, and that will tell you. And similarly, in the case of this theorem, if one believes, so I'm not telling you actually whether curvature is blowing up here or there. The theorem allows that. It's an open problem to actually show that even though the metric is not being destroyed, curvature, in fact, blows up. But regardless, you can sort of draw a little hypersurface here. That sort of, is the space-like hypersurface before curvature is above your threshold. And this is sort of a statement up until that hypersurface, which is completely within the realm of classical general relativity. And yes, if you want to sort of say what happens when you're really, really there, yes, you have to go beyond. But already, sort of, if you just interpret the statement up to here, it tells you that something very, very different from, let's say, Schwarzschild happened. Okay? So, of course, it goes without saying that, anytime we talk about singularities in general relativity, we don't, that does not commit ourselves to believing general relativity at the singularity. All these statements have interpretation up till whatever your favorite cutoff is. And in fact, the whole point in sort of making these statements about the dynamics of the Einstein equations is so that they have such an interpretation.
There was Andy, I think, is next in line. Andy.
So this is a not completely unrelated question, but we don't generally believe that general relativity is exact. There should be some corrections, r squared or derivatives of r, which just from dimensional analysis will only become important at incredibly high curvatures, and there's certainly no experimental evidence that such things don't exist. Now, so it wouldn't have been a problem, it wouldn't have been a logical inconsistency of general relativity if there had been naked singularities. in fact, it would have been a wonderful thing. We wouldn't have had to build the Large Hadron Collider. We could have just pointed our telescopes into the sky and seen what happens at very high energies. So the puzzle to me is, why is cosmic censorship so close to being, maybe it's not exactly been proven, but why should it even have be close to being true? Why couldn't it, it would be logically acceptable if smooth initial data generically formed singularities, and then we could learn a lot about super Planckian physics cheaply. So why does it work so well?
It's a very good question, and in fact, somehow, when there was much less experience, I think, when these conjectures were sort of formulated, perhaps how profound it is for them to be true was maybe not appreciated sufficient. I mean, one thing that I would mention...
Didn't they feel that there was some, Wheeler used the phrase, the greatest crisis of all time, as if it were a problem if cosmic censorship were false? I think they...
Well, okay, that's a very philosophical question. Is it a pro, is it good, is it bad? I'm not going to answer that. But
okay.
What I will happily answer, though, is the following. If you look at most systems of nonlinear hyperbolic PDE, that sort of are of similar nonlinearity to the Einstein equations, to the Einstein vacuum equations. So Einstein vacuum equations are reach equals 0, but let me give you another example of equation, the Euler equations of compressible fluid mechanics, which again, you can write it as a nonlinear, in the irrotational case, you can write it as a nonlinear wave equation. It's slightly more nonlinear, but anyway, it's of similar form. These type of nice statements, even sort of the analog of stability of Minkowski space, is not true for that system. Arbitrarily small solutions will form shocks, and then who knows what happens. Okay? Completely intractable. And for some reason, the Einstein equations, even though they're nonlinear, even though they do form singularities, somehow, there are these conjectures, which if true would mean that the singularities, given that they're singularities, it's the best possible scenario. Yeah, that is amazing. I'm not going to, I don't know why, it may indeed be true. I'm not, it seems that it may be true. It's amazing that it seems that it may be true. I don't have a, philosophical answer if that's good or bad, or, it does seem that it may indeed be true, and it is profound, yeah.
I think we shall have to call a halt at this point, otherwise we'll lose our opportunity for tea. So let's thank the speaker again.